Continuing on physical chemistry, we're beginning chapter 17 now with section 1. Now we're going to talk about kinetics, which is newer than thermodynamics. There are two kinds of kinetics. The first is physical kinetics. For physical kinetics, we have transport processes, rate mechanisms, but this is more for engineers than chemists. For example, let's say we have some sort of region in a system, we'll call it A. Then we're talking about going from A to A, so nothing's really moved around. So example would be like diffusion and fluid dynamics, fluid mechanics, and so on. That's not really chemistry. There's also chemical kinetics. This is what we're going to be talking about. So here we're going to be talking about the rate the chemical reactions happen, or the mechanism of how chemical reactions actually happen. So we're going to have something from going from A to B. Now, as far as reactions goes, there are two kinds of reactions. There's homogeneous reactions, or homogeneous reactions. These occur in one phase. For example, let's say we have a mixture of gases, so gas phase solution, or a mixture of liquids, liquid phase solution. But then there's also heterogeneous reactions. So in this case, they're going to happen in more than one phase. For example, let's say we're going to burn gasoline in an engine that has a catalytic converter. The gasoline is in the vapor phase, and so is the oxygen, but the catalytic converter is a solid. Another example would be hydrogenation of unsaturated hydrocarbon with a solid metal catalyst. So we're going to start here with ethane and add some hydrogen gas. So these are both gas. We're going to use a solid catalyst like nickel and so on, and then we're going to get C2H6, ethane. So let's talk about rate of reaction. So let's say we're going to have some sort of substances, A amount of substance A, B amount of substance B, etc., reacting to give you E amount of substance E, and then F amount of substance F. That's supposed to be a lowercase f right there. So we're going to be talking about a closed system and homogeneous. And then lowercase t we're going to say is time. And then the rate of conversion we're going to use capital J. So we're going to define, remember a 3-line equal signs means defined as. So we're going to define J as minus 1 over A times the derivative of the number of moles of substance A with respect to time. The reason for the minus sign is because we're losing the reactants. And likewise, this should be minus 1 over B times the derivative of the number of moles of substance B with respect to time. Notice these are equal to each other because of these denominators. And then for the products, we're going to have 1 over E times the derivative of the number of moles of substance E with respect to time. And that's going to be equal to 1 over F times the derivative of the number of moles of substance F with respect to time. Notice the products are positive because we're creating products in the reaction. So remember, capital V is volume in this case. So we have rate of reaction is equal to R, which is defined as J over V. So the rate of reaction is the rate of conversion divided by volume. Now this nomenclature here, A in these square brackets, that's the concentration of A, the molar concentration of A. So that's intensive. So rate is going to be equal to minus 1 over A times the derivative of the concentration of A with respect to time. And that's going to be equal to minus 1 over B times the derivative of the concentration of B with respect to time. That's going to be equal to 1 over E times the derivative of the concentration of E with respect to time. That's going to be equal to 1 over F times the derivative of the concentration of F with respect to time. So those are all equal to each other. So pick whichever one you happen to have the numbers for. So we have minus 1 over A times the derivative of the concentration of A with respect to time. And that is the rate of consumption or the disappearance of A. That's how fast we're using up the reactant. And then likewise 1 over E times the derivative of the concentration of E with respect to time. E is a product, so that's the rate of formation of substance E. Now of course R has to be positive then. And of course R is intensive. So like I said already, the left side is going to be equal to the rate of the disappearance, and the right side is going to be equal to the rate of appearance. So R is going to be in moles per liter per second, or molarity per second, or just molarity times seconds to the -1. Lowercase s is seconds, obviously. So now let's talk about rate laws. So we're going to have a rate law. I'm going to say the rate of reaction is going to be proportional to the concentration of substance A to the alpha power times the concentration of B to the beta power, etc. for all the substances, L to the lambda power. So alpha, beta, lambda, these are numbers. They're usually integers, but they can sometimes be half integers too. So R is going to be equal to a constant. So remember we had proportional before. To make an equal sign, we're going to put in some sort of constant there. So we're going to have alpha to, or the concentration of substance A to the alpha power times the concentration of B to the beta power, etc., all the way to the concentration of L to the lambda power. So K, in this case, is just going to be some arbitrary constant for now. It's not the Boltzmann constant that we learned about before. This is going to be the rate constant. K is going to be dependent on both temperature and pressure. Now, it depends on the reaction, of course, but a lot of times you'll find it's highly dependent on T for temperature, and it can be weakly affected by P for pressure. Obviously, we'll be explaining why later on. So for now, we're going to ignore the dependence on pressure because it's not nearly as strong. Now, a rate law should be determined experimentally. You can't just sort of guess. So in the formula above, we're going to say that alpha is the order of the reaction with respect to substance A, and beta is the order of the reaction with respect to the substance B. So like, let's say alpha is 2, then we'll say it's a second order reaction with respect to substance A, and if beta is 1, then we'll say it's a first order reaction with respect to substance B. So the overall order of the reaction is just adding up all the exponents, alpha plus beta, etc., all the way to lambda, or however you go. But like I said, alpha, beta, and lambda, they can be any real number, even though they're typically integers or half integers. So again, the order is determined experimentally. You can't just tell from the balanced equations. So here are some examples of rate laws. So here's the reaction. We're going to have hydrogen gas plus iodine gas to give hydrogen iodine gas. So this is the observed rate law. R is equal to K times H2 times I2, the concentration of hydrogen times the concentration of the iodine. So in this case, it works out nicely. It's the first order with respect to the hydrogen, and it's first order with respect to the iodine. So it's overall second order, because 1 plus 1 equals 2. Here's another reaction. Here's hydrogen plus bromine gas to get hydrogen bromide. Uh-oh, should that be a 2 there? Uh-oh. Okay, minor typo. Anyway, so let's see. So here's how the rate law comes out. We're going to say rate is equal to K times the concentration of I2 times the concentration of bromine. Wait, shouldn't that be Br2 right there also? Oh boy. Br2 to the 1/2 power divided by 1 plus J times the concentration of the hydrogen bromide divided by the concentration of the bromine. And so J is another constant, just like K. So as you can see, that one's kind of complicated, even though it looks similar to the one we just did. Here's another example. Here's 2N2O5 gas just decomposing into 4NO2 plus O2, both gases. The rate is simply going to be dependent on the concentration of the reactant, K times the concentration of the N2O5. Here's some more examples, just so you can see it comes out different. So here's a acetaldehyde, CH3CHO, decomposing to methane and carbon monoxide. The observed rate law, K is equal to R equals K times the concentration of the acetaldehyde to the 3/2 power. So there's an example of a half integer I talked about before. Here's another one, 2H2O2 aqueous, so that's what hydrogen peroxide. And then with an iodine catalyst, iodide ions catalyst, going to 2H2O, water, and oxygen. The rate law is dependent on both the concentration of the hydrogen peroxide, but also the iodine, because it's a, catalyst. So in this case, obviously, the concentration of the catalyst, the iodine ions, can be used in the rate law. Just remember, don't confuse the rate constant with the equilibrium constant. So let's talk about mechanism. We're going to start with reactant or reactants. That's what this S means. It means possibly more. It doesn't mean solid. So we're going through a variety of intermediate steps. Could be 0 or more intermediate products. And then finally the product or products. So the sequence of these elementary steps, the intermediates that constitute the overall reaction, is called mechanism. For example, let's look at that last one again, or one of those again. So we have 2N2O5 decomposing into 4NO2 plus O2. That's the overall reaction. Now, here's a proposed mechanism, a plausible mechanism. So here's the overall, so we'll say 2N2O will be in equilibrium with 2N2O plus 2NO3. So this is one elementary reaction. Just remember, NO3 is not the nitrate ion. NO3 is the exotic because it's a radical. So it's unstable. That's why it's an intermediate, not a product or anything. And then we'll take that NO2 and the NO3, and we're going to react it to give NO and O2 and NO2. And then finally, we'll take the NO plus the NO3 and make 2NO2. If you add all those up together, you end up with the original reaction. 2N2O5 going to 4NO2 plus 2O2. So that shows that it's at least somewhat plausible. Now notice the first elementary reaction, it has to happen twice for each time the sequential reactions happen. But then these, also remember this NO and NO3, these are intermediates. They're not reactants, they're not products. Intermediates on each side of the equations, of course, for your mechanism should cancel out. So intermediates don't necessarily last long. They're created and then they're used up quickly. But we can use spectroscopy or something to identify intermediates if we want to, investigate whether the proposed mechanism is actually happening or not. So mechanism for a reaction isn't necessarily unique, though. There can be different routes for the same reaction to happen. If there is evidence to support that a mechanism is true, then we say the mechanism is plausible. Now we're going to use the lowercase cursive s for the stoichiometric number. So remember how I said this first equation happens to have twice for all this other one. So we're going to say for this first the step is going to be, the stoichiometric number is going to be 2. And then the sequential ones, the stoichiometric number is just going to be 1. So add them all up, though, with the correct numbers, and you still end up with the original equation. So we're also going to say this nu here is a stoichiometric coefficient. So, where was I? So back to the original equation here. Oh, it's on a different page. Well, then the 2, 4, and the 1 are the overall reaction, are nu 1. So each step in the mechanism, the top 3 equations in the above example, this is an elementary step or an elementary reaction, or a single step or a simple reaction. So here's another reaction. Let's say we have ethylene, which is C2 or CH2 double bonded to CH2, and then we're going to have 1,3-butadiene. So here's CH2 double bonded to CH, single bonded to CH, double bonded to CH2. You put them together, you're going to get cyclohexene. So this reaction happens in one big step. So we can use a really fast laser, a pulse laser, like 1 femtosecond pulse, to watch for these intermediate steps in the fast reactions, see how they actually work. Now in thermodynamics, we just need to know the 2 states, the initial state and the final state. So time doesn't matter. Now there's also such thing as a pseudo-order reaction. Like let's say we have sucrose, CH12H22O11, plus water, and then we have hydrogen as a catalyst, and that's going to go to glucose and fructose. We're going to say, okay, the rate is equal to K double prime times the concentration of the sucrose times the concentration of water to the 6th power times the concentration of the hydrogen. So the overall order of the reaction is actually 8. But the thing is, since the sucrose is completely dissolved in the water is actually in excess in practice. So the concentration, it doesn't actually change that much during the reaction. So we couldn't actually do this experiment very well without plenty of water. So if you're in practice, if you're going to be doing this reaction, you're going to have excess water. So we're just going to assume that the concentration of the water is constant and use a different K. So then we just have R is equal to K prime times the concentration of sucrose times the concentration of the acid. Now, the concentration of the acid is also constant because it's just a catalyst. It's not a product or a reactant. So since it's constant in your system, it's not going to really affect your rate. So what we can do is just get rid of that too and say, well, in practice, the rate is equal to the constant times the concentration of the sucrose. So we'll say this reaction is pseudo first order because the conditions in which it happens, it seems to be first order.